I'd like to give to present some results on strong right-convex functions of higher order. All the results I'm going to present here are results of a joint work with Nelson Merentes, Kazimierz Nikodem, and Zsolt Páles. In the talk, we will proceed according to the following schedule. First, we will consider the basic concepts related to strong convexity. Then we will give the definition of strongly right-convex functions of higher order. And after that, I'm going to present three results related to strong right-convex functions of higher order. First, characterization of right-convex functions of higher order, then a decomposition theorem for them, and finally, characterization theorem for strong right-convex functions via derivatives. Let's start with the basic concepts. These concepts were considered also during this meeting by several authors. The first one is the concept of strong convexity, which was introduced by Poljak in 1966, or maybe even earlier. As it was also mentioned in the talk of Kazimierz Nikodem during this meeting yesterday, this means that as the geometric interpretation of convexity is that a function is convex if and only if if you consider each 2 points of the graph of the function, then the graph of the function is below the segment, line segment between these 2 points. Now, it is a stronger requirement here, as you can see. Instead of the convexity inequality, we assume here that the left-hand side is less than or equal to, this is in the convexity part, minus positive c times t times 1 minus t. This is or positive here, x minus y square. It is easy to see that it is a stronger requirement. In fact, then the graph of the function have to be a certain parabola going through these 2 points. And of course, the parabola is not uniquely determined by these 2 points, so it depends on the value of c as well. But anyhow, this is the geometric interpretation of strong convexity, that the graph of the function is not only below the line segment between the 2 points, but below a certain parabola below the 2 points. And this property is valid, of course, for all 2 points of the interval. Of course, if we write c equals 0 in this definition, then we get back simply the defining inequality of convexity. As you see, f of t x plus minus t y is less than or equal to t times f of x plus 1 minus t times f of y for all x and y in the interval I, and for all t between the interval 0, 1. Okay, in the next step, we are going to proceed to right-convex functions. It is well known that if we interchange the role of x and y in this inequality and add this inequality and the inequality obtained this way, side by side, then we get the defining inequality of right convexity. That is ftx plus 1 minus t times y plus f of t times y plus 1 minus t times x is less than or equal to f of x plus f of y, which is the defining inequality of right convexity. It is easy to see that convexity implies right convexity, but it can be proved that the other direction is not valid. Using this concept, an analogous definition to the strong convexity with modulus c can be formulated. This definition was formulated recently by Nelson Merentes, Kazimierz Nikodem, and Sergio Rivas. Assuming that not this inequality, which is on the blackboard, is valid, but a stronger inequality again, that is the left-hand side is less than or equal to this part minus 2 times a positive number times t times 1 minus t times x minus y square. Okay, then the next concept can be obtained if we write in the defining inequality of convexity t equals 1/2. As you know, then we get the definition of midpoint or Jensen or Jensen convexity. The corresponding strong convexity concept is, or strongly Jensen convexity with modulus C is f of x plus y over 2 is less than or equal to f of x plus f of y over 2 minus C over 4 times x minus y squared. That concept was used maybe earlier as well, but at least it was considered by Weyer or Vial in 1982. In the following, we are considering, or we will consider, higher order versions of these concepts. Let's consider first the higher order version of strong convexity and strong Jensen convexity. These concepts were introduced and investigated by Roman Guerre and Kazimierz Nikodem in a recent paper. The definition of strong convexity of order n with modulus C can be given with this formula. The strong Jensen convexity of order n with modulus C can be given using this formula. It is easy to see that in the case when n equals 1, these definitions give back the previous concepts on the previous page. Yes, of course, here, concerning notation, this is the divided difference of the function f belonging to the points x0 and so on, x n plus 1, and this is the linear difference of order n plus 1 of the function f at the point x with step size h. Roman Guerre and Kazimierz Nikodem proved several results on strongly Wright-convex functions and strongly Jensen convex functions of high order. Mainly motivated by these results, we started to investigate exactly the case which is missing here between them. As you remember on the previous page, we talked about strongly Wright-convex functions with modulus C, and in the higher order case, it is, so to say, missing here, so between them. So we started to investigate strongly Wright-convex functions of higher order. Let's consider first the definition of strongly Wright convexity of order n. Yeah, such a real valued function defined on interval I is said to be Wright-convex of order n if it satisfies this inequality again with the delta operator. Now the step sizes are different, so h1 and so on hn plus 1. Assume that it is greater than or equal to 0, and you can guess what will be the definition, what will be instead of 0 on the right-hand side here. Yes, C will be positive constant, and the left-hand side is greater than or equal to not 0, but C times n plus 1 factorial times h1 times and so on n plus 1. It is easy to see that also in this case, in the case when n equals 1, we get back the concept of strongly or strong Wright convexity with modulus C. Another remark to these concepts is that during the whole talk I will talk about strong convexity or strong convexity of higher order. However, if you omit the assumption of the positivity of C here in these definitions, in all of the definitions, then you will get also some notions which make a sense. And in fact, all the theorems I'm going to prove here are valid in this case. So in fact, we can even omit this positivity, this assumption for the positivity of C. And then we can talk about, in the case when C is positive, then strong convexity. If the case when C is negative, approximate convexity. And if C is equal to 0, then convexity, Jensen convexity, Wright convexity, or higher order convexity, and so on, respectively. So maybe in the future it will be better to use or to talk about convexity with the modulus C, and then we don't have to assume the positivity of C. Okay. Let's consider the results I promised to you. The first one will be characterization of higher order right convexity, strongly higher order right convexity via right convex functions of higher order. The theorem is the following. Using the O notation, if a function mapping into R and defined on the interval I is strongly n-right convex with modulus C, but let's say if we have such a function, then if and only if the function g that we get so that f of x minus c times x to the power n plus 1 is n-right convex. So which means that if we have a strongly n-right convex function with modulus c, and we denote it by f, then f of x minus c times x to the power n plus 1 will be n-right convex function, and vice versa. If we have an n-right convex function g, and we consider the function f of x, which is g x plus c times x to the power n plus 1, then we get a strongly n-right convex function with modulus c. So this is real characterization. The main steps of the proof. In fact, the proof is rather simple. Yeah. First, we prove the direction if f is strongly n-right convex with modulus c. Then we define the function as it is given in the theorem. And then doing the simple calculation with the delta operator. Using the linearity of delta, we get this equation here. And then, according to the assumption for f, we get that this term here is greater than or equal to c times n plus 1 factor I times h1 times and so on, hn plus 1. And this term is here, it is well known, is equal to this term here. So we got this part of the statement quite easily. The other direction is also similarly simple. If G is n-right convex, then if we consider f as it was given in the theorem again, then using the linearity of the operator delta again, we get this property here. And yeah, this term is equal to 0, since G is an n-right convex function. And yeah, plus this term here, which we get from this one, gives this equation which implies the validity of the other direction in the theorem, which means that the theorem is already proved. Okay, let's consider the next statement. This statement will be a decomposition theorem for strongly right convex functions of higher order. In this decomposition, we will use higher order convex functions that we touched already. As you remember, it was in the case when C is equal to 0 in the definition of strong convexity. But I repeat it here just for simplicity. This definition was given by Hofs in 26 and later on by Popoviciu in 34 and 44. Yeah, and the real valued function defined on an interval I is said to be convex of order n if it satisfies this inequality where we consider on the left-hand side, again, the divided difference of the function f based on the points x0 and so on, x n plus 1. And the other definition, if the definition of polynomial functions of degree n. Such a function is called a polynomial function of degree n if it satisfies this equation here, where the delta operator is the linear delta operator here again. To formulate and prove our theorem, decomposition theorem of Gyula Maksa and Zsolt Páles will be useful for us. They proved the decomposition of n-right convex functions using convex functions of higher order and polynomial functions of higher order. They proved that a real valued function defined on an open interval I is n-right convex if and only if it has the form f is equal to h, a convex function of a higher order, and plus polynomial function of, let's say, a convex function of order n plus a polynomial function of order n. They also proved that on the rational numbers, this p part is equal to 0. Gyula and Zsolt Páles proved that this decomposition is also unique. Based on and strongly related to this theorem, we can prove the decomposition for strongly right-convex functions of higher order. The statement is the following. If a real-valued function defined on an open interval I is, but let's say, okay, let f be a real-valued function defined on an open interval I. F is strongly and right-convex with modulus C if and only if it is of the form f of x equals to h of x plus p of x plus c times x to the power n plus 1, where h is a convex function of order n, p is a polynomial function of order n, and yeah, c times x plus c times x to the power n plus 1 depends on the constant c which is given. Here we have this property as well, and according to the theorem of Maksa and Páles, we have uniqueness for the representation here too. So now we have the decomposition of strongly and right-convex functions. With right-convex functions, we have a decomposition theorem for them. And the third statement that I promise you will be characterization of such type of functions using generalized derivatives. The generalized derivative we use here is this derivative. More precisely, this is the lower form of the derivative. So let's consider this definition for a moment. Now, it is the d lower n f of xi is equal to the limit inferior of delta n h1 hn f of x divided by h1 hn f of x, such that this limit inferior is taken in a quite certain case. I will draw a picture for that, then it will be understandable for you. So the function is, let's say, somewhere here. This is also not important for us. We will just take the point xi here. And this limit is, in fact, an interval limit. And this is, as I will give a remark on it soon, is strongly limited to the Dinghas derivative. And this limit is taken so that the point x is here. As you may see there, it is less than or equal to xi. And the endpoint of the interval, which is x plus h1 plus and so on plus hn, as it is here. And we take the limit, or we consider this limit inferior on that case that these endpoints of the interval are approaching xi. We take the values of this expression here in this case, and we just simply take the limit inferior of this expression. Of course, this expression always exists, so it is, we don't need any requirements for f to get it. If the limit of the expression also exists in this sense, in this interval limit sense, then we denote it by d and f xi. It is easy to see, not so easy, but it is not very complicated to prove that this term, this d lower n f xi, is a generalized derivative. This means that if a function is n times differentiable in the common sense, then of course this d lower n f xi also exists, and it is more important, this d lower n f xi is equal to the nth order derivative of the function f at the point xi. Moreover, in this case, not only this lower derivative, but also this derivative exists, and of course it is equal to the nth order derivative of the function f at the point xi. And as I mentioned you already, this derivative is also a generalization of the so-called Dinghas interval derivative, which was introduced in 1966. So let's consider then a result related to this derivative. It is an earlier result from a joint work with Zsolt Páles. This theorem characterizes right convex functions defined on an interval I. Such real valued function defined on I is n right-convex if and only if its n plus first lower, let's say, d derivative at each point is non-negative. Based on and related to this theorem, we can prove a characterization of strongly n right-convex functions with modulus C as well. The theorem reads as follows. If n is a positive integer, C is a positive real number, and f is a real valued function defined on an interval I, then f is strongly n right-convex with modulus C if and only if, you may guess, I think, or that if its lower n plus first interval derivative at each point in the interval I is greater than or equal to not 0, but C times n plus 1 factorial. So this means that we proved all, or we presented at least all three theorems, the two decomposition theorem, two characterization theorems, and one decomposition theorem for strongly right-convex functions of higher order. Finally, I would like to give you some references. Yeah, we already wrote a paper on these results. This is the last one here, which is now accepted for publication in Opuscula Matematica, and will appear, I think, this year in the last issue of the journal. Here is the paper, which was the main motivation for all investigations, and here are some other references I mentioned in the paper, and this is the original paper of Polyak, where strongly convex functions or strong convexity for functions was defined. So thank you very much for your kind attention.